Okay, the last time, of course, we were talking about various ideas of the array queue. And in lab yesterday, I think people were thinking way too hard about how to implement this. All this is, it's, okay, we need to keep track of the front. Well, that'll always, with the idea number 1, that'll always be index 0. So we don't really need to keep track of it. We need to keep track of the rear. That's where we add things. And we've got an array that's used as a container. Keeping track of the rear, that's just an index. That's like the value, like the integer representing which index it's at. But every time we dequeue, we have to like shuffle everything down, right? Like we need to take this light blue one, it gets removed. We'll have to move the blue one down, and then the gray one down, and then the black one down, and update rear. But, you know, the in queue is easy. We just tack it on to the end. But the problem, oh my goodness. The problem is that shuffling down is linear in terms of the amount of computation required, right? If I've got a million things in my queue and I dequeue one thing, I got to move all million things down, which is trouble. That's a lot of work. Where we saw with the linked queue, well, we didn't have that. But then we had this other idea where, okay, instead of always having the front be index 0, we can have that like incrementing too. Kind of like how rear increments, we can increment front. Every time something gets dequeued, if the front was 0, we dequeue, well now front is 1. Next time we dequeue from front, which is 1. So we remove 1 and then make it 2, and so on. We'll have to just do some extra fancy bookkeeping, but if we do that, you know, our in queue is order 1 and our dequeue is order 1. But you're gonna get a sense that we're going to be wasting a lot of space, right? Because if I start dequeuing, all of the parts of the array here that get dequeued, if front is like index 4, indices 0, 1, 2, and 3 are useless. Like, and we can't even use them anymore. They're just wasted space. So that's not very like efficient, I guess, right? Why would you have to move them? Well, in idea 1, we move them. Unless in idea 2, then we just update front. So we don't have to shuffle them down. Yeah, sure, you could, but then that's still going to be linear time every 10. I mean, there are a number of workarounds here. This is just idea number 2. But when I go through the tester, I get things saying test name. That's weird. Yeah, I don't know. That's something. I don't know, but let's focus on this. Does reducing the amount of linear times you need to do well, yeah, but we still. You're really going to have to reduce the amount of linear work a lot in order for us to get away with saying like, well, we've amortized it down, so it's not really going to matter. Kind of like with expand capacities. Yeah, expand capacity is linear time, but it, you know, it happens so infrequently that not that big of a deal. So this idea here, we kind of end up wasting space. Like this index 0, it can never be used again. And the suggestion was, well, maybe every so often shuffle them down. Okay, yeah. But suddenly we're now throwing more linear work in when still at the end of the day, the linked one, the linked queue, the dequeues were all really simple. They were just our constant time. So 1, is this implementation correct? Will it work? Is it a queue? Say yes. Good. Yeah, it's a queue. There's nothing wrong with this implementation. But how often do we need to call expand capacity? Because in idea 1, we'll have to do expand capacity if we ever get full. But you know, if I have like, let's say size 10 array, and I do 5 in queues, 5 D queues, 6 in queues, then I need to do expand capacity. No, that's not true at all. If I have size 10, if I do 5 in queues, 5 D queues, and then 11 in queues, we'll have to call expand capacity then. But the problem with this, because of that wasted space, the DQs don't give us, it doesn't free up any room on the far side, on the rear side. So we're going to end up having to call expand capacity more frequently. So, you know, so yeah, well, how about this? Here's idea 3. Idea 3 is based on idea 2, but there's a trick to it. So we're going to use an array. We're going to keep track of the front index and the rear index, right? So just kind of like this one, but the difference that we're going to do is if there's space at the front of the array, not the front of the queue, at the beginning of the array, we're going to loop the indices back to 0 for our rear. So what we're going to do is we're going to pretend, let me make sure I'm recording, yeah. We're going to pretend our array is a circle. It's not. It's a linear thing, but we're going to pretend it's a circle. So in the example, pretend we have an array of capacity n. The indices would be ordered like 0, 1, 2, 3, 4, da, 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 n minus 2, n minus 1, 0, 1, 2, 3, 4, 5, 6, n minus 2, n minus 1, and so on and so on and so on forever, because there's no end. It's like this circle. We just keep looping back and back and back. The index that comes after n minus 1, or pardon me, the index that comes before n minus 1 is n minus 2. The index that comes after n minus 1 is 0. The index that comes before 0 is n minus 1, and the index that comes after 0 is 1. So take this circular array with 7 things in the front. So here's the idea. Here's the front. It's index 0, and the rear is the next available spot. So 0, 1, 2, 3, 4, 5, 6. So I guess we have 7 things in there. If I NQ, it would just go here. But if I DQ, like this will be the kind of like the state of things, right? So I did 5 DQs. So now here's front, here's rear. Now I'm going to do 8 more NQs. 1, 2, 3, 4, 5, 6. But I only have 6 spots left in the array. But what we do is we just go, yeah, but once you get to 12, just loop back to 0 and then 1. So I just always keep track that rear, like rear can end up being a smaller index than front. So we can go from the front and then it just loops back to index 0. So this is a clever way to take this idea, but then just say like, well, if I ever get to the end, just loop back to index 0. What comes after, let's say this is 0, 1, 2, 3, 4, 5. It's only 5. So if I NQ 2 things, well, the one goes here and the next goes in index 0. Then if I NQ another one, well, I have to call expand capacity. But the front before expand capacity is index 1. And the rear, I guess, would also be index 1. So I guess that's when we need to call expand capacity. Oh, this should be fixed already. Did it not get fixed? Okay. Yeah, okay, fixed. Any questions of the circle array idea? Remember, it's not really a circle. It's not a circle at all. We're just pretending it is. What comes after n minus 1? What comes after the last thing? The first thing. Right? Does it really? No, but we're just pretending it does. It is, yes, it's beautiful. So, okay, there we go. Oh, someone's hand's up. What is up? What's the question? Oh, hand is down. All right. Oh, okay. All right, you got a question. I got you. We'll give you a moment. So yeah, the idea 3 is basically idea 2 with a catch. Well, wait a second. Okay. So would we expand capacity when we have more items to put in the queue than there are spaces? Exactly. Right? The front and rear, who cares where they are? But if I have 10 things in my queue and the capacity is 10, we need to expand capacity. Okay. If you need to call expand capacity, do you transfer it back so that no longer a circle? Well, it's never really a circle, but sit tight. I think we're going to answer your question in a moment. Just a bigger circle, yeah. So here's what we'll do. After a bunch of NQs and DQs, it will loop around like this. So, what? Okay, after a bunch of NQs and DQs, it will loop around like this, except it's not looping around. What? Front is 1, rear is 5. All right, well, this sentence is clearly not describing what's happening. I have to go double check which images are there. Someone should go add an issue, that there's an issue with idea 3's images on the linked queue, on the array queue, because I'm pretty sure those are just the identical. Yeah, they're the same as these. Yeah, it's probably a copy paste error on my part. Okay, so modulo. So we've seen this already, the percent sign. It's like a remainder, right? So if I say 4 mod 2, well, that's 4 divided by 2, and tell me what the remainder is. So 4 divided by 2 is 0, and the remainder is 0. There's nothing left. So 4 mod 2 is 0. 5 mod 4, well, we can take 4 out of 5 once, but then we're left with a 1. So 4 mod 5, 5 mod 4 is 1. I hear a boop. 4 divided by 2 is not 0. That's also a bug. Yeah, someone should go fix that as well. Well, you can go make a GitHub issue or correct this and make a PR and make an amazing contribution to the course content. Yeah, okay, so 4. Okay, 7 divided by 8. Well, that's 0 with a remainder of 7. Right? So, like, if I try to take 8 out of 7, I can't. So I can only do that 0 times, but what's left? Well, 7. There's 7 things left. So 7 mod 8 is 7. And, you know, we may have already been using this before, right? To check, like, mod 2. If something mod 2 is 0, then we know it's evenly divisible by 2, which then means it's an even number. So if something mod 2 is 0, we know it's even. If something mod 2 is 1, we know it's odd, right? So we've been using this before. Do you have YouTube videos on how to report to GitHub? I don't, but there's probably millions from other people. Okay, so let me put it this way for a second. Let's say I had an array of size 8. No. Let's say I had an array of size 10. Go here. Open up Paint. All right. So we've got array. Okay, so we've got, I'm just going to draw, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So we have indices. I'm going to draw these in like gray or something. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Okay. Let's say rear is currently 0. Everyone pay attention. This is big. Rear is 0. If I add something to the queue, where does it go? Rear. 0. No, not 1. 0. So the thing would go here, right? And then we increment rear. So rear would now be 1. So this is rear. If I add something to the queue, where does it go? One. Good. And then I increment rear, right? So I'm going to increment rear to be, okay, well, rear is equal to rear plus 1. Well, 1 plus 1 is 2, so rear is now 2. And then we enqueue it, goes there, and so on and so on and so on. And then finally here, if I have, what is the length of this? The length of this is 10. Okay, so let's say I'm on 9. I add something, it goes in index 9, and then we need to increment rear. Rear equals rear plus 1, which is what? 10. Well, it should be 0, but in reality, 9 plus 1 is 10. So rear would be 10, which is a problem. But what is 10 mod 10? How many times can we get 10 out of 10? And what's its remainder? Yeah. So I'm wondering if I can do something like, okay, what if we do like rear equals rear plus 1 mod len, where length is 10. So let's think about it. Let's say rear is 3. Okay? So rear is 3. I increment it, it becomes 4. And then what is 4 mod 10? How many times can I get 10 out of the number 4? 0. You can't. And then what's left over? 4. Yeah. Let's say I have 8. Let's say it's 8. Okay? And I increment it to 9. Okay? What is 9 mod 10? Well, how many times can I get 10 out of 9? Well, 0. And what's left over? 9. Right? So 8 equals 8 plus 1. Okay, R equals R plus 1. That's 9. 9 mod 10. Well, how many times can I get 10 out of 9? 0. And what's left over? 9. So rear becomes 9. But as soon as I try to make it 10, I go, okay, well, rear equals rear plus 1. 9 plus 1 is 10. 10 mod 10. Well, how many times can I get 10 out of 10? Once. And what's the remainder? 0. So this would mean rear now becomes 0. So this mod is the thing that's kind of giving us a hand in just looping back to the beginning. And that's all we're gonna do to just add this looping back feature. Because if you were worried, like, oh, check if it's the length, and if it's greater than that, you need to make it set to 0. Yeah, you could do that, but the mod's kind of doing it for us, which is pretty cool. So this is how you set rear in a circular way. Yeah, assuming I understand the question. So you might have been thinking to yourself, well, a solution would be like, okay, if the new rear equals array dot len or something like that, then new rear equals 0, right? You may have been thinking, okay, well, we need this condition. Then we ask if 0 is null. Well, I mean, there's a lot of things we can, so what you're asking now is like, well, what if something's there and we need to actually expand capacity? So there's a number of ways we can go about doing that, and we'll get there. But yeah, you may have been thinking we need this, okay, this conditional check on rear, which, yeah, that would totally work. There's nothing wrong with this. But we actually can we don't even need the conditional. We can just easily ask if it's, just do the equation, calculate the value based on the expression containing mod, which is pretty cool. So there's the mod idea. Someone better go submit an issue about this because I might forget if you don't. All right, so, okay, our rear is currently 9. Okay, this is just explaining the same thing. So we use this formula. Add 1 to rear, mod it with the length of the queue, and that's our new rear. That's what it is. So if rear is 9, we use the expression, we end up with 9 plus 1, mod 10, which is equal to 10 mod 10, which is equal to 0. So rear is now 0. Perfect. If rear is any other number less than 10, the number is not divisible by 10, meaning the mod will effectively have no difference, right? If I have any number less than 10, or if I have any number less than the length of my array, if I say mod the length of the array, I can't get anything out of it. And the remainder will be, it's like what the value is, what the original value is. So this is pretty cool. So with the special expression for updating rear, do we need it for updating front? Well, yeah, because remember, it could be the case that front is like here and rear is somewhere else, and I increment front. If I DQ, well, front's gonna have to loop back too. So it's not just rear that needs to be updated with this, front does as well. So we gotta be careful there. And with this idea, will we ever run out of room in our array? Yeah, obviously. If I have 10 spots and I try to enqueue 11 things, it's not gonna work. All right. Okay, what is this? Warning, sometimes good enough is good enough. All right, okay, this is a big warning. Okay, in this array queue implementation scenario, number 3 is quite clearly the superior option and is not overly difficult to implement. However, as you continue in computer science and work in more complex problems, sometimes ease of implementation and maintainability becomes very important. Better algorithms always exist. That's like a saying, okay? There's always a better way. And a subpar implementation may be good enough, especially when you have a problem space that's small enough. So you're like, oh, you know, my problem's linear, but maybe I can find a log n solution. Well, great, but if n is only ever less than 100, who cares? It doesn't matter. And if I have a part of my program that's like n cubed, well, then the linear time thing is not even going to matter at all. The n cubed thing is the thing that wastes all the time. So computational complexity is very important. I hear that. In the case, does that make sense to keep track of the size? Front and rear? I don't know, you tell me. Computational complexity is very important, but sometimes in practice, we may lose sight of the forest through the trees, right? So this is like, we get so obsessed with finding a better algorithm when it doesn't matter. If you can change your algorithm from n squared to n, then you should probably do it, right? So if you have a quadratic algorithm, something that takes n squared time, and you can make it linear, that's a really good improvement. But if the updated algorithm, finding and thinking of that better algorithm is going to take ages, 2, implementing it is complicated as hell, 3, it's not even going to be used that much, and 4, you know, if you've got a complex implementation, that's a lot harder to maintain, right? So sometimes a really cool, well-finessed solution is great and all, but if it's too complex for anyone else to look at, they're going to go like, oh, I don't want to think of that. So just as a warning, at this point in the course, we haven't seen it, like, this isn't that applicable at this point in the course. This is a warning for the future as you go. But even worse, if you're trying to save a few flops, that's a floating point operation. It's a way you can like measure processor speed. Save a few flops here and there, great. But if it's distracting you from the more important issue, you probably should move on. And then Donald Knuth, who's a very, very, very famous computer scientist, said, and here's a quote. Okay, what does maintain is like, oh, someone later needs to look at your code and maybe make some little changes to it here or there, scale it up a bit or something. But if they get your code and they're like, what the hell? Like, what the hell is going on here? That's a problem. You want it to be nice, clean, so they look at it and it's easier to maintain. Okay, here's, that quote. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their program. And these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunity in that critical 3%. Long story short, computational complexity is super important. And for the content in this course, yes, it is. But as you go on, sometimes good enough is good enough. Okay? Gibberish code's the best. Okay, expand capacity. So we have something that looks like this. Suppose we enqueue. Front is 2, and rear, remember rear is always the next available spot. And in this case, well, if rear is 1, and then I enqueue something, both front and rear are now 2. In a job with coding, how do I know which to pick? Experience. The faster one. So here, both of these, both the front and the rear are now 2. So now I know the queue is full. There's a couple of ways I know the queue is full. One, when the count, the size, is equal to the length. Yeah. Or when the front and the rear are the same. That's how we know it's full. And then we need to expand capacity. However, we cannot just double the size of the array and copy the contents over like we did before. And now there's an aside on this going into more details, but we can't just double it and copy over the contents. Because let's think about what would happen if we did. So, okay, great. So the array was 4 before, 0, 1, 2, 3. So now we got 4, 5, 6, 7. So now we have 8 spots. But the problem is the front is 2, the rear is 2, and we've got this giant gap in the middle of our queue, right? We've got, okay, 2 is followed by 3, followed by 4, which is nothing, 5, which is nothing, 6, which is nothing, 7, which is nothing, and then suddenly, oh, 0 has something, 1 has something. So this is obviously not going to work. This is bad. Because really what I would like is to have, okay, 2 can maybe stay here, fine, as the front, 3, but these bits here, the 0 and 1, should be taken and moved here. So rear should then be updated to be 6. Right? So instead, we copy the elements in the contiguous part. Like this. This is much better. Or an even better solution. You know what? Saying it's an even better solution, maybe it is, maybe it's not. But what we could do is, instead of even just saying like, okay, well, loop it back, just start copying the front to index 0. Front plus 1 to index 1. Front plus 2, index 2, and so on. So we basically take this, make it go to index 0, and then copy the queue over in the correct order. So doing another enqueue, we add to the element to the rear, update rear with rear equals 0 plus 1, mod queue length. Yeah, cool. So does that idea make sense now? Because the basic idea isn't overly complex. You've got, okay, enqueue, dequeue. The magic is thinking about it as the circle array, and then having to be careful about our indices and expand capacity if we don't think about this critically, if we don't take our time to think about it, if we just jump and copy paste expand capacity like we have in the previous with the stack, we're in trouble. So we need that like fancier expand capacity, which we'll look at. So, will this implementation work? Is it a queue? Is it correct? Say yes. Yeah, of course. What's the computational complexity of an enqueue now? Just think of this for a sec, right? Like here, we're in this situation, let's say. Well, you just add it to rear and then increment rear. So it's constant. And a dequeue is constant as well. But of course, when we do the in-queues, we might have to do that expand capacity. But relative to idea 1 and idea 2, we're going to probably call expand capacity as often as idea 1, but less often than idea 2. But the problem with idea 1 is that we had that shuffle, so the DQs were linear. When this one, the DQ is constant time. Just take the thing away from the front. Done. Increment front. That's it. So we now, with just this clever thinking of how to just think of our array and how we're storing the information, we suddenly get this much better implementation. So this would be an example if you're going like, yeah, but it's more complex. Well, this is probably one of those 3% of the times where you're like, no, you should probably... This is a simple way to have a linear constant time DQ. Sure, we have expand capacity, but it's going to get called once for every time we've like filled it up. So like we amortize all that work and we're in great shape. Yeah, okay. Let's talk about implementing it. So all the code is available at the bottom of the page in the download links, and we can go have a look here even. It's array queue. So here we go. Can you see this well? I think I might have made the font too small. No, the font's there. Okay. So what do we got? Well, okay. Array queue T implements a queue, meaning we need to have in queue, DQ, first, size is empty. So, okay, our default capacity, fine. A queue of type T, it's generic. It's an array of type T. Front is an int, rear is an int, and size, we'll just keep track of size because otherwise it's going to be complicated to calculate that because you're going to need to do the calculation of like, well, what's the front, what's the length, how do you, the difference, and then add this where, we'll just update size every time we enqueue or dequeue. So our constructor, front, rear, and size start as 0, and then we make a new empty array of object and then cast it to type T. So we have an array of type T, and it's empty. So our enqueue, here's the enqueue. If size is equal to length, we need to expand capacity. We'll look at that in a moment. If it's not, queue at rear equals element. Rear equals next index. I did this next indexed thing here. Index thing here. I don't know if I did that in here though. No, I didn't. So here's the enqueue in the code I have here. Enqueue T element, check the size, call expand capacity. Otherwise, queue at index rear equals element. Rear equals rear plus 1, mod the length of the queue, and then increase size. If you go look at the push for the array stack, it's identical with the exception of the mod part. That's it. That's how it's going to work. So the array stack's push is nearly identical to this. Just as a note, in my implementation, I made a private method called nextIndex that just takes whatever the index is and does that calculation for me. Just because I like to have, even though you say like, well, that's such a simple little method. You're right, but I like, I don't know, if someone didn't know what they were looking at, if I gave someone code and they see like, oh, next index of rear, this method name makes it really obvious what this is doing, where if you see rear equals rear plus 1 mod the length of the queue, that might be a little confusing to someone who's not familiar with what this code is. So I just did it that way because I don't know, I like it that way. Never be afraid to add private methods if you find them handy. Okay. So, okay, there's the enqueue. But of course, expand capacity. All right, let's go look at expand capacity because this can get weird. All right. We'll take our time here. First step, make an array of size twice the size of the original. Okay, so far this is like It's very similar, right? Let's go here. Let's go array stack expand capacity. Make the new array. We've got the for loop, and then we update stack. So here, well, we've got that. We've got the for loop, but the contents are a little different, so we'll come back to this. And then q equals the new q. So the only differences really are we've got this extra bookkeeping here that we'll get to, and the way we're addressing this is a little different. So I say new q at index 0. All right. So new q at index I 0. Get q at index front. All right. So I'm putting, I don't care which index front is. Front could be 78 for all I know. But I'm putting the contents of q at front into index 0 of the new q. Okay, that's what that line does. Then I increment front. I get the next index of front. And this next index, remember, all it does is it does the mod if I need to. So this is doing that looping back like the circle array. So the difference here is because this stack and the new, because the new stack and the original stack were always 0 to the end. I could go from I 0 0 1 1 2 2 3 3. That was good. But here that's not the case. We've got I front. But then we increment both I and front. So with the array stack, yeah, after we're done, we increment both things, which is the same thing, I and I. Here we just, well, we need to make sure we're incrementing both. New q at index I at front. New q at I plus 1, well, yeah, I plus 1 to front plus 1, and so on and so on and so on. So this goes through and copies everything over, but it does it such that the front is always going to be index 0. Meaning I can say, okay, yeah, great, front is now index 0. Because clearly when I'm going through this, I'm changing what front is. So I need to reassign front to be, okay, the front of the new q is 0. Rear will be, well, whatever the size is, conveniently, because it starts at 0, right? So if I have a queue of size 50, and I copied everything over to the new array of size 100, well, if the front's 0, the rear is going to be 50 because there's 50 things in there. And then we just update what queue references. The field queue references, well, that new one we just made right here. So let's talk about the bits again. Create a new array twice the size. Loop through the contents of the old queue and put it into the new queue. But we got to be fancy with our indexing. Then we update front and rear based on the fact that we got fancy with our indexing. And then just say queue field, queue, this thing here, yeah, you're referencing the new queue that was just made right here. Then, it's NC here. Yeah, I'm doing it with the fancy mod length. Span capacity is a little different. Yada, yada. Okay. Take your time with this one. Make sure you understand the nuance here. This is going to be an important thing you're going to want to look into. If you don't understand it, the good news is you can take this code, you can run this code, and you can see how it's working. This is definitely one of those important things you're going to want to make sure you wrap your head around before we carry on in the course. All right, DQ, how does it look? Well, okay, if it's empty, we can't do it. Get the element from the front, increment front, might have to loop around, reduce the size, return the element. Empty, get the thing from the front, increment front, reduce the size, return the element. There you go. And then, of course, testing. Oh, and okay, if this is DQ, first is going to be the same, but way easier, actually. Not the same. Look at this. Look at that. Oh, so easy. Size, well, is empty? Well, is it 0? If it is, then it's empty. Size, well, that's just the size. Here's my private next index. Just, I liked it. I've got a fancy 2-string here. Make sure you're looking at these 2 strings and you get a sense of how they work, because you're going to definitely want to write them for yourselves. So there's the 2-string. Here's an equals. This, if you can, have a look at this and see if you can make sense of it. If you're wondering what the hell, that's not too important. It's just, I wrote it here for you. And then a hash code because. So if we want to go test this stuff, well, we can take the same testing code that we did for the linked queue, but change it to array queue. So here, look, this is the array queue playing code, right? That you can go download, I think. Maybe not yet. If we go to linked queue, yeah. If we go to the bottom of linked queue, there we go. And here's the bottom of, come on, of array queue. Here. These are identical. The only difference is, oh, instead of a linked queue, I said, oh, it's an array queue, and I gave it a capacity here of 5. And then, oh, I also kind of check expand capacity by in queuing more things. But because remember, we can do this because it's a queue. My queue is a reference to a queue. Is it an array queue or a linked queue? I don't care. It's a queue. And if it's a queue, I can get its size. I can ask if it's empty. I can 2-string it. I can enqueue things. I can dequeue things. I can get the first from things. If it's a queue, it can do this. I don't give a shit if it's an array queue, a linked queue, an idea 1 queue, an idea 2 queue, or any of those things. I don't care. As long as it can do the things a queue's got to do, that's all I care about right now when using it. Of course, when it comes to implementing it, we care because we're implementing it. But yeah. Can you explain this? All it means is, oh, and the equals, right? Here, all it means is like, it doesn't even, it doesn't even care what the type is. Just take it and cast it of something, of an array queue of whatever type, right? I mean, in this case, because it's of type T, it will be type T. But this is written like very generally. And again, this is one of those things that I'm kind of like referring to when I say, don't worry too much about this, okay? By all means, look at it, see if you can make sense of it, because it's, you know, if you take your time with it, it'll make sense, but it's still pretty heavy. So yeah, playing code, there we go. Next, the bag. Great. So, we saw stacks, we saw queues. Stacks were very limited in what we can do, right? We can push and pop. That's it. Queues are limited too. We can enqueue and dequeue, but with a stack, it almost feels a little bit more limited. Not really, but it kind of feels like it because all the action happens from one end, right? So you might say, well, what if I want the thing in the middle? Well, get popping, because you can't just get it. You have to pop things off first to get to the one you want. You can't just access it. A queue, you know, same kind of idea, right? You enqueue and you dequeue. But yeah, sure, the action's happening at 2 different ends. But if you say like, well, I want the 5th thing in the queue, not the first thing in the queue, tough. That's not what a queue is. If you want that, fine. Dequeue 5 times. There, you got it. But if you want to be able to just access things arbitrarily in your data, then, or in your data structure, in your collection, then you're not using a queue. Like you don't want a queue, you want something different. Because the queue, the rule of the queue is you add and remove from one of the 2 ends. The stack is you add and remove from the one end. But of course, there's nothing saying we can't make a data structure that's more general, that's like, no, you can add them wherever you want. You can remove them from wherever you want. Kind of like a list in Python, right? Remember the lists in Python? You can just like append to the end, or you could specifically say like, okay, insert here. So you could say specifically which index you wanted to put the thing in. There's a whole bunch of things you could do. So a list is far more general, or like the Python list is far more general than like a stack or a queue. Like you can do more with it. You can use a list like a stack. You can use a list like a queue. But you can't use a stack or a queue like a list, right? Hopefully that makes sense. So a bag, it's a little bit of a different idea here. This is my nice little Ziploc bag thing. So, bags are more general than stacks and queues. We have a lot more flexibility on where we add and remove elements from. So we kind of like to think of a bag as just like, okay, it's a collection of information, right? By default, a bag doesn't really have any ordering, right? I mean, we can make it have an ordering, which we will. We'll make an ordered bag, but its implementation may be with some sort of linear collection. So like I might be using an array to build a bag, but the fact that there's an index 0, 1, 2, 3, 4, 5, the order doesn't actually matter. It doesn't mean anything. But the idea is the information in the bag has no order, even if they kind of do, but they don't. Same idea with a set, right? Information in a set doesn't have an order. And you're going to say, yeah, but that one's at the beginning of the set. Yeah, but the fact that it's there doesn't make it different than a set that didn't have that one at the beginning, but it had that one at the end, you know? So order doesn't matter for these things. So what are things we want to do with our data structures? Remember, we always want to add things, remove things, get the size, and check if it's empty. So we want to add to the bag. How should we add things and where should they go? Remove. Where do we remove them from? How do we do it? You know, these are kind of big questions because there's a lot of like, well, it depends. And we'll pick up here on Tuesday, I guess. But yeah, the bag is the next data structure we'll be playing with. Any last questions before we wrap up? Okay, well, in that case, is the cutoff date exactly 7 days? Yeah. Yep. So if you put it in at 11:56, no good. All right.